Okay, before we move on, it's important to understand a little bit of how to interpret and how to implement the conservation of the form momentum. So, just like in um, classical conservation of three momentum, what you do in relativistic mechanics, in particular when you're conserving form momentum, is that you add up all the form momenta of all the components of the whole system that you're looking at, that you're studying. Okay, and you do this before the interaction, so before the collision or whatever sort of forces are applied, mutual forces exist between the constituents of the system, and then you add up all the form momenta of all those particles before the interaction or interactions, and then after the interaction or interactions. And it's if you basically take into account the whole system, that is, if the system is closed, okay, um, if it's isolated, then the total form momentum before must equal the total form momentum after the interaction. Okay, let's talk about photons for just a little bit. How do we handle photons in this form momentum picture? Well, let's start with Einstein's energy momentum relationship, which I've written again right here. And so for photons, their masses are equal to 0, okay? And so this means that their energy is equal to their momentum times the speed of light. But we've already shown that beta is equal to PC over E, which in this case is equal to 1, right? E is equal to PC. So this implies that massless particles, like photons, travel at the speed of light c. Okay, so we know that this is true for photons. Photons are particles of light, and so this is one of the tenets of relativity, is that they travel at the speed of light c. But this says that any particle, any massless particle, travels at the speed of light. Okay, what is the form momentum of a photon? Well, it's just equal to, in general, E over c for the zeroth component, the temporal component, and p for the spatial, little p for the spatial components. But note that since E over c is just little p, right, for a photon, E over c is just little p, you get for that from there, then this means that the magnitude of the form momentum of a photon is equal to p squared minus p squared, which is equal to 0, which we should already know because it's also equal to mc. Okay, which is and since it's massless, it's equal to 0. So this shows that the magnitude of the form momentum of a photon is equal to 0. However, that doesn't mean that the form momentum doesn't carry energy and momentum. It does. Its energy is E over c, which is just its energy is just pc, and its momentum can be calculated. But it carries both energy and momentum. It's just that the magnitude of its form momentum is 0.